All right. Now we are on the next page, which is page 211. And we're going to talk about limacons. So limacons are the more general form that cardioids come from, right? So a cardioid was like A plus or minus A, and then cosine theta or sine theta. Limacons are like the parent function from which a cardioid comes. So we're going to have just a constant plus a coefficient times sine of theta, or a constant plus a coefficient times cosine of theta. Limacons have really neat graphs. One particular type has a really neat graph. The other one's kind of just there. So if you look at these four, I bet you can tell which ones are interesting. And let me put check marks next to the interesting ones. They are this one and this one. So these are interesting because they have what's called an inner loop. So an inner loop is, I mean, you can look at it and see, it's the little loop that's kind of like inside the bigger loop. So both of these have inner loops. And we're going to talk about how you get an inner loop, where they come from. In fact, if you look at these right now, you can kind of see a pattern that will give us an inner loop. So for the two we put check marks next to, we have 5 minus 8 sine. So the constant is 5. The coefficient is, I'm going to say the magnitude of the coefficient. So the coefficient is 8. The coefficient is bigger than the constant. For the other one with an inner loop, we have 6 plus 11 cosine. So the constant is 6, and the coefficient is 11, so the coefficient is bigger again. So it looks like if the coefficient is bigger than the constant, we will get an inner loop. We're going to find out that that's actually true. So let me just like jot that down. So if coefficient is greater than the constant, inner loop. And that's a big deal. As we go through this, you're going to learn, so you don't have to memorize that. You're going to learn what's making the inner loop happen. And then as long as you can remember how to graph in rectangular, you will definitely know if this thing has an inner loop or not. So other things to notice though. So if the constant is bigger than the coefficient, then you will not get an inner loop. That's kind of the opposite of that. And then they're working the same as our circles that were centered on an axis tangent to the origin. Also, they work the same as cardioids, obviously, because cardioids are limacons. So if we have a negative sign, it's going to be predominantly on the negative y-axis because sine tends to go with y. If we have a positive cosine, it'll be predominantly on the x-axis because x tends to go with cosine. And then the opposite will be true. Positive sign is on the positive y, negative cosines on the negative x. All right, so let's actually graph one of these and see what's going on. All right, so we have r equals 2 plus 4 cosine theta. I'm just going to go ahead and graph that. So 2, it goes up to 6 because you can add 4. It'll go down to negative 2 because you can subtract 4. We need to go to 2 pi, which means the middle of it is pi. And then because there's some important features, I'm not going to label pi over 2 and 3 pi over 2, but we know what they are, right? We're counting by pi over 2's here. So I want to graph this. So it's cosine. It's going to start at maximum here. It's positive cosine, so it starts at maximum, I guess I should say. And that. And then we can fill it in. So when you fill it in, you want to be careful because you want to have kind of an accurate graph so that you can see what's going on. I don't know why the line got so thick there. I just got an Apple Pencil for my stylus. As like a short review, I would say that it is in fact worth 10 times what my old stylus was worth. So it's like a really expensive stylus, but if you have the money and you're going to do a lot of stuff like this, I think it's probably worth it. Like if you're going to be taking notes on an iPad all the time, like yeah, I would definitely hesitate, but I would eventually buy it. So I've been hesitating for years and I eventually bought it. Okay, so the zeros of this graph, just like for rose curves, the zeros of the rectangular graph, right? So we have theta and we have r. The zeros of this graph are going to be the tangent lines because they're going to be theta equals something of the graph that we're going to make. So first, what I need to do is I need to figure out when that happens. So I need to know when r is equal to 0, because when r is equal to 0, that's these 2 points, right? We're on the theta axis. So r equals 0 means that 2 plus 4 cosine theta equals 0, which means that cosine of theta is -1/2. And if cosine of theta is -1/2, then you can think of your unit circle, right? So the x coordinates are -1/2, so you kind of know it's 2 pi over 3 and 4 pi over 3. So let me write those down. 2 pi over 3 or 4 pi over 3. So I'm going to dot those in as tangent lines. But look at the rectangular graph that we made. If we made it well, which we tried to, then you can kind of see, right? Like it looks like the x-intercept of it, because it's a nice ratio, like one of the famous ratios. We're looking for basically the closest angle to pi over 2 that's in the second quadrant, right? And that we know is going to be at 2 pi over 3. And then the next time it happens, it's really close to 3 pi over 2. It's actually the closest unit circle angle to 3 pi over 2 that's in the third quadrant, which would just be 4 pi over 3. So you combine all the things you know, and life just gets easier. That's why you have to know all of those things. So we're going to dot those in, and then we're going to go through the process of turning the rectangular graph into the polar graph, which is what you basically always do. So let's dot in 2 pi over 3. Okay. One of the things you'll find is in terms of finding the tangent lines, the polar graphs are really generous, I guess, right? They're very forgiving. So if you try to solve cosine of theta equals -1/2 and you get it wrong, and you think like 5 pi over 3 is one of the angles, that's not right. But when you plot it, because the rectangular line falls in the same place as 2 pi over 3, like you'll still get the line. So in fact, when I graph this, I'm going to follow 2 pi over 3 into the origin, and then I'm going to follow 5 pi over 3 out of the origin, because I find that a lot easier to do. And then I'm going to do the same thing for pi over 3. And these, you don't need to go all the way out, because these are only important at the origin. So like, I don't need to go all the way out to like 7 or whatever, because I'm not going to use it out there. And then I'm going to follow 4 pi over 3 out. Okay, so those are my tangent lines. And now the question is, what am I doing? All right, so what color should we use? Let's use, I don't know. There like aren't a billion colors. I'm gonna use this like sort of light green color you'll see in a second. So when r is equal to, when theta is equal to 0, r is equal to 6. That's my color. So I'm going to decide, what should I count by? I'm gonna count by ones. 1, 2, 3. Why would I count to 3? Let's say, I'm gonna do it anyway. 3, 4, 5, and then 6. That's gross. This is not a great color. Let me erase that. We're using a different color. Let's use let's go with the old standby. Let's go with black. All right. So 1, 2, 3. My neighbor's, I don't know, mowing his lawn or something. So I don't know if you can pick up that. 1, 2, 3. This will be 6. All right. Here we go. So when theta equals 0, r is equal to 6. So we're going to put a point. There's actually something that really nice that happens with these. So the tangent lines are where r is equal to 0. It kind of coincidentally is the case that the other nice values that you can plug in also sort of fall on the like other part of the tangent line, right? So we got 2 pi over 3. 5 pi over 3 is going to be a nice number to plug in. We got 4 pi over 3. Pi over 3 is going to be a nice number to plug in. So if I take pi over 3 and I sub it in, I'll get 2 plus 4 times the cosine of pi over 3 is 1/2. So I get 2 plus 4 times 1/2, so I get 2 plus 2 plus 2, so I get 4. So what I'm going to do is I'm going to go up here and I'm going to plot, I think there. Let me count that. 1, 2, 3, 4. Yes, that's good. So these points, you don't really need them. It's just better if you have them, I guess. Now we're at pi over 2. So at pi over 2, we're going to be at 2. So let's fill this in. So we go from here to here, and then from here to here. And now the fun begins. As we go from pi over 2 to 2 pi over 3, you can see on the rectangular graph, we're going to go from 2 to 0. So what happens is you just kind of, whoa, where are you going? You just kind of go like that. And then if you go in along a tangent line, you're going to come out along a tangent line, and we're going to head for -2 pi, because that's what the rectangular graph says to do. So we're looking for -2 pi. So you're looking at pi, that's the negative x-axis, but you're going to walk backwards. So you're going to walk along the positive x-axis until you get to this point. So we go in along this tangent line, we come out along this tangent line. And then usually what I do is once I have half the graph, I just mirror it over the axis. So I'm going to like talk through it a little more, but what I would do in general is I would just finish this thing, right? So I would go like this, and then when I get here, I'll be at this point. And then when I get out here, I'll be at 3, 4, and I'll aim for that. And I feel like things are about to go poorly. And then kind of okay. So like what happened? Let me change color and just like show you. So once we got to pi, between pi and 4 pi over 3, so like on this part of the graph, so between pi and 4 pi over 3, we traced this part of our graph. And then between 4 pi over 3 and 3 pi over 2, we traced this part of our graph, which turns out to be this part of our graph. And then we finished from 3 pi over 2 to 2 pi. We went here to here, and we filled in like one extra point along the way. All right, so this is probably long, so I'm going to attempt to stop the video here, and I'll obviously be back with more.